All right, this is lesson 1-2 for Honors Algebra 2, and we're obviously talking about solving linear inequalities. So let me first get into some terminology that comes in handy when especially when we're dealing with word problems, real-life application problems involving inequalities. So we're used to seeing the symbols. I've got those over here in green to the left, but what are some ways that these might be identified using words? Well, some of them are pretty obvious, like we probably are hopefully very familiar with this as greater than. All right, but you might be looking at a word problem and it could be worded as is more than. Means the same thing, but I'm just trying to give you a heads up as to different phrases that could be used to describe these inequalities. Obviously, this is less than. Could be known as is fewer than. This is greater than or equal to. But we may see it in a word problem. It means greater than or equal to, but maybe it's worded as is at least. Or it may be called is no less than. All three of those phrases refer to the same inequality symbol, greater than or equal to. And then obviously this is just going to be the opposite, so less than or equal to. Or instead of is at least, is at most. And is no more than. All right, so just a little bit of a review, but trying to help you out for when you do get to some word problems. Sometimes these phrases are used in reference to these symbols. And so just giving you a little bit of a heads up there. Now, when you get to these problems, you're going to be translating phrases, word phrases, into an inequality. And then once you've found your inequality, then you need to solve. So letter A says 15 less than. Less than refers to subtraction. 15 less than the product of 2 and a number is less than. Notice the little tricky there, is less than is how we refer to, or we called it is fewer than, but notice the verb there. That indicates that we're actually going to be using an inequality. So 15 less than the product of 2 and a number. So I'm going to say this is my product of 2 and a number. 15 less than that would be subtracting 15 is less than 33. And then that sets up the inequality, and now we need to solve. So we solve inequalities just like we do equations, with one big rule that we have to keep in mind. If we end up dividing or multiply by a negative number, we have to remember to reverse the direction of the inequality. So solving this, I would add 15 to both sides and then divide by 2. And that would be my solution. Well, sorry, I forgot. That's an inequality, not an equation, so this should be less than. Okay, so here's another one. The quotient refers to the answer to a division problem. The sum of 4 and the quotient of the sum of 4 and a number. Okay, so let's just see that part. The sum of 4 and a number. And the quotient of the sum of 4 and a number and 9, so we're dividing by 9, is at least -7. So remember, going back to our previous slide, we said is at least is another way of referencing greater than or equal to. And now we solve it by multiplying by 9 on both sides. and then we would subtract 4 from both sides, and we get our solution. And we talked in class today about this idea of interval notation, and that's something that's going to come up more and more as you get into higher math classes. It's another way of expressing inequalities. I think I'll use the next problem, and we'll show you some interval notation, and we'll introduce it today, and it's going to be used quite a bit throughout the course of the year. All right, the difference, of course, is subtraction. 5 times a number and 2. So 5 times a number and 2 being subtracted is greater than the number. Okay, now we'll solve it. I'll just go ahead and subtract 5 in from both sides. And since I'm dividing by a negative number, I have to remember to switch the inequality. So I'm going to be dividing by -4. So that makes positive 1/2, and this is going to become less than. And then n, or if you prefer, like I typically do, I like to put the variable on the left. So this would also be true. N is greater than 1/2. So let's just take the we'll take the next problem where we actually have to draw a graph, and I think I'll use that to illustrate interval notation. All right, so here we're just solving inequalities. So let's just get right into it. We're going to subtract 13 from both sides. I'm going to divide by -6 on both sides, and I get my solution as x is greater than -2. So the direction says to solve each inequality, then graph the solution on a number line. So here's a number line that represents the solution set. I typically put 0, and then I put the number part of my answer, the boundary part, as in reference to 0, would be on the left. And I'm going to show the solution set is all the numbers greater than -2. So this is called an open interval. Since -2 is not part of the solution, I leave the circle open and I shade to the right. Well, this is called an inequality notation, but this is the same thing in what we call interval notation. An interval is it's like a range of numbers that has a left side and a right side. But in this particular case, our left side's pretty easy to determine. We see that it's -2. The right side of this interval, well, it extends into positive infinity. This arrow indicates that the solution set just keeps going on and on in a positive way, positive infinity. So the interval notation for this, to show this using interval notation, it would look like this. It looks kind of like an ordered pair, but it's actually, think of kind of like bookends, even though this really isn't a bookend because it never stops, but it's kind of that same idea. You have a left bookend, the smaller number will always go on the left, and then your bigger number will always go on the right. Just think about how the number line runs, smaller to the left, bigger on the right. So if the circle is open, then we use a parenthesis. If, and I'll just change the problem, maybe if it had said or equal to, meaning that this would be a solid, then the way we show interval notation for or equal to is instead of a parenthesis, we put a bracket. So it would look like this if it was or equal to. So you never bracket infinity. I mean, think about that. There's no way that you could ever include infinity in the solution. It never stops. So if you put infinity in interval notation, it will always have a parenthesis by it. But sometimes numbers like this, -2, is part of the solution, and we show that with a bracket. Okay, so a little extra lesson that we covered today was on interval notation. All right, so for letter B, I'm going to distribute -3 first. And I'll add 3 to both sides. I'll divide by -6. And once again, that rule of division or multiplication, by a negative number causes me to reverse the inequality. So the graph would look something like this. It's a range of numbers, all the numbers that are bigger than 4. And using interval notation, we're introducing that concept today. We would say 4 would be the left boundary and infinity would be the right. And it's an open interval, so we use parentheses around 4. Very good. All right, for letter C, we want to get the variables on the same side, so I'm just going to add 13y to both sides, and I'm going to subtract 4 from both sides, and we'll divide by 8, and we get the solution is all the numbers, the range of numbers that are greater than -5. So once again, relative to 0, it's going to be an open interval, so open circle shading to the right with interval notation that would be -5 on the left, and it's approaching positive infinity going to the right. Here, to clear denominators, we're going to use the lowest common denominator, which is 12. So I can divide 3 into 12 to get 4. And then I'm going to multiply 4 times both of these terms. That's 16z plus 12. Over here, I'll divide 4 into 12 and get 3. And I'll multiply 3 times both of these terms. That's 18z minus 6. So I'm going to solve for z. I subtract 16z from both sides. I add 6 to both sides and divide by 2. I get 9 is less than or equal to z, or you could turn it around and say z is greater than or equal to 9. So we're supposed to graph this. So relative to 0, this time it's greater than or equal to, so it's going to be a solid shading to the right. And then our interval notation, just for practice, this time 9 is part of the solution. This is a closed interval, so I use a bracket. 9 would be on the left side of the interval, and it's still approaching positive infinity on the right. Okay, so we wrapped up our class today by looking at a couple of real-life application problems. Here is a company that pays someone to Enrique's company pays Salim to advertise on Salim's website. So Enrique is getting advertising attention. He pays for it by putting an ad on a website. Salim is going to get $15 a month plus 5 cents every time a visitor clicks on the advertisement. What is the least number of clicks? Okay, remember we talked about, I'll just refer back to that slide. At least means greater than or equal to. So that's going to be the inequality that we use in our problem. The least number of clicks in order to earn at least $50 a month. So to answer the question, the question is what's the least number of clicks? That's what I'm going to let my variable represent. X equals number of clicks. And we'll just go ahead and say per month. All right, and so we want to earn at least $50. So it's going to be greater than or equal to 50. It could be more than 50. Could be more than 50, but it has to at least be 50 at a minimum. All right, so what else do we know? 5 cents every time a visitor clicks, so 5 cents times the number of clicks. And we get this $15 a month flat fee. Doesn't really matter how many clicks, it's just going to be a flat $15. So that sets up our inequality. So now we're ready to solve for x. Subtract 15 from both sides. And we'll divide by 0.05 on both sides. And we get our number of clicks must be at least 700. And so we typically like to answer a word problem with a phrase. And we could say something like this: he would need at least 700 clicks. All right, and then we set this one up. This is another advertising type problem. Jen is advertising in a blog. Jen earns 3% commission on every ad he sells. Plus, there's a flat $250. So if you don't understand the idea of commission, there's a flat rate that's paid. And then every time, just to encourage people to advertise, we give people 3% for every ad that is sold. It's usually the way salespeople make their money is on commission. So if the average amount of money that a business spends on an ad is 500, how many ads must he sell each week to make a salary of at least 700? So we need to define a variable. So the answer to the question, how many ads must he sell, we're going to let that variable be the number of ads. We just let the variable basically answer the question. All right, so let's come up with this inequality. Well, we know that we've got to come up with at least $700. So this is in terms of money earned. We know that the target that we're trying to hit is at least 700. Hopefully it's going to be more than that. At least Jen hopes so. But that's the bare minimum. So what do we know? Well, we know he's going to get 250 regardless. 250 is like a flat fee. We also know that on top of that, he's going to get 3% for every ad sold. And most businesses, according to our problem, spend $500. Okay, so we can write that as 3% of the product of $500, which is the average amount per ad, times the number of ads, which we're calling X. All right. And so we just went ahead and worked this out, but that's the answer to part A, write the inequality. And so now let's just go ahead and we'll finish this off, and this will take care of one of your homework problems. So if you go to 0.03 times 500, and then you subtract 250 from both sides. And divide by 15. Okay, so what we came up with is X represents the number of ads he must sell. According to this, he's got to sell at least 30 ads. And that's it. So I would encourage you to do this. If these word problems kind of give you trouble, it's always a good idea to, while you're doing your homework, even though we worked through this in your notes, see if you can do it again without any help after you've gone away from it for a little bit, just for extra practice. It's always a good way to get better, is just to practice these, and you'll see a lot of similarities from one problem to the next. But I would suggest if this was really, really challenging, you really didn't understand, see after you've given a little bit of time after notes, go back and later and see if you can do it again and get the correct answer. Okay, so that should wrap up our notes, and so that is the assignment that we will check next time. And if you have any questions, let me know.